Welcome back, everyone. Here's another example where we're going to use normal to approximate binomial. So we're going to use a different distribution to approximate another distribution. So binomial will be approximated by normal. I have done another example in a separate video. Please feel free to watch that and then continue into this one. So this is example 2 or another example of this idea. So hopefully you know that the normal distribution is a distribution that looks something like this. So we call this is the normal curve of that distribution where we have symmetry about the mean. So mean is right here. That's right at the center, call it mu. And this is the normal curve. So we want to use this idea to approximate binomial. We know binomial is a distribution that satisfies the following conditions where we have n number of trials. For example, in this problem, we're looking at 1,000 results in twins. So that is your number of trials. And we're also trying to look at probability of success of this event. So the probability that a birth results in twins is estimated to be that. So we have a success of the event, and the failure will be the complement of 0.016. So once these criteria are satisfied, that's a binomial distribution. So let's suppose that we have the following. So we know that n is the number of trials, that's 1,000. We also know the probability of success of the event. So let's use the variable x. So x represent that the birth results in twins. Let's go ahead and write that down. Which means the probability of the success of this event, p of x, which we call a little p, that's going to be 0.016. Then q is the failure of this event, that's 1 minus p. So that's 1 minus 0.016. And then if you use your calculator, you'll see that this is about 0.984. Okay. All right. So we have n, we have p, we have q. Now, since it's a binomial, we can find the mean, which is mu, that is going to be determined by doing n times p. So we know n is 1,000. You multiply that with 0.016, you'll have your mean to be about 16. And then sigma is the standard deviation of binomial. This will be the square root of np cubed. So this will be square root of n times p. So that's 1,000 times 0.016 q. That's going to be 0.984. All right, so put all of this in your calculator and you'll get a value of 3.97. All right, so I'm keeping it 2 decimal places for this. So all of these stuff is important when we approximate this using the normal distribution. Okay, so what do we want? Well, we want to know what is the probability that at least 5, but no more than 15 births out of the 1,000 results in twins. So here's what we want. We want to know what is the probability that X, meaning birth results in twins for this number of people, at least 5, but no more than 15. So 5 meaning that's the lower bound, the upper bound is 15. So you want X to be between 5 and 15. Okay, so hopefully that makes sense. Now, if you were to use the binomial probability formula, so note that for binomial, we find probability of such event, big X equals little x, that's going to be n choose x, that's of the n trial, you choose x number of success, times p to the power of success, q to the power of n minus x. So if you were to use that for this problem, you're going to have to find probability that x is equal to 5 plus the probability x is equal to 6 plus all the way up, counting up to probability that x is equal to 15. And that is a very tedious problem. So that's why we're going to use normal to approximate, because if you use the rule of thumb to test this out, you'll see that normal is a good approximation to this particular distribution. So that's what we're going to do. We're not going to do it this way. We're going to use normal to approximate. So we're going to say this is going to be approximated by normal. But before we do that, we need to extend our interval. So here, suppose, so we know the mean is 16 for this problem. It's called, that's the x value. And let's suppose x equals 5 is right here. So imagine looking at a histogram for the normal distribution. So if this is 5, when you draw this rectangle standing at 5, you extend the interval 0.5 in both directions. So this value is 5.5. Sorry, that's not 5.5. Apologize for that. This is 4.5. So I guess I need to zoom in a little. So this is the rectangle, or number of people have the birth results 5 for this event. So this is going to be 5. Then this is 5.5, and this is 4.5. So you know the length of this rectangle is 1. So this is 4.5. Okay, so hopefully you understand what I'm trying to do here. And then, of course, you have the next rectangle for 6 people, 6 birth standing right here. That's for 6. And then for 7, somewhere right here, you have these tiny little rectangles. And then as you continue on to the next x value, which is 15, we're after. So let's suppose the rectangle of at 15. So maybe it's right here, right? So let me just try to draw as close as possible. Let's just say that, right? Let's just assume that's there. So this is standing at 15. So this is x equals 15, which means it's side a little bit right here. This is at 14.5. And then this right here, this, I hope you can see that, that's 15.5. So we want all of this area. So we want from, I guess that's not the right color to show you, but we want cover 15 birth, right? At most 15 and then less. So we want all of this area to be covered under the normal curve. So because of that purpose, the continuity purpose of the normal curve with a discrete variable, we want to make sure we extend our interval here. Instead of looking at 5 to 15, we're going to look at probability that x is between 4.5 and 15.5. All right, so now that we have that down, let's go ahead and now find the corresponding z values for these x values. So our next step is to write down, this is the probability that z is between two numbers. So we need to find those two values. So for the first z value, let's say for x equals 4.5, what is the z for that? We know we use the formula z is equal to x minus the mean over sigma of the standard deviation. So for this problem, we know our mean is right here, 16, and sigma is right here. So I'm going to substitute them and use the x value 4.5 to get the z right here. So we have this is equal to x is 4.5 minus the mean divided by sigma. That's 3.97. And then this will give us about, I believe this will give you about negative 2.90 after you put this in your calculator. Okay, so that's the z value that goes here. Now let's find the next z value for 15.5. So again, using the formula, z is equal to x minus mu over sigma. Here we're finding a z-score for 15.5. So substitute that for x minus 16 over 3.97. So this will give you a z-score of negative 0.13. Right, so that's the number we're going to substitute right here. So let's go ahead and make those substitutions. So for the first z-score, this is negative 2.90, and this one is negative 0.13. Okay, so I hope this is making sense so far. So remember, we need to find probability or the area between these z values using the z-score table. But first, let's simplify this. So what this statement means is that we know this is the probability z is less than or equal to negative 0.13, because that's the greater z value, minus the probability that z is less than or equal to negative 2.90. Now, why is that? Why do we take this and take away the area of this? Well, here's why. So negative 0.13 is the z-score for this value. So when you find the area reading of negative 0.13, you get the area from here covering all of that under the curve. So all of this region. But we're not interested in all of that. We just want in between, right? So you find that area first. So whatever this is, you're going to subtract with this area because this will correspond to everything from here. So for this x value, the z is negative 2.9. So we get everything from here to below all of that. So we can subtract away, so we get only just between them. That's what we want. So now let's go ahead and do that. So let me take you back to the z-score table and show you how to read these numbers. All right, here's the z-score table we're going to be using. Be mindful that this table will read area under the normal curve, but to the left of z value. So if you're looking at a z-score, you're going to read off everything to the left of it, all of that area. Okay, so the first one we wanted to look at is negative 0.13. Let's go ahead and scroll down to -1. So we're going to look at right here, negative 0.1. So scroll down for negative 0.1. That's right here. So that is negative 0.1. And then 0.03. So because that will give us negative 0.13. So that's right here. So we scroll down, see where the two things intersect. So here you go. So I assume I was coming down this way. All right, so I'm looking at this area right here. So negative 0.13, that's the area. So that's the probability of z is less than negative 0.13. So we said that the area is 0.4483. So let's go ahead and write that down. So this is 0.4483 minus, now we go back up and read of this one. So vertically, we're going to look for negative 2.9. Horizontally, it's just 0, 0. So negative 2.9. So that should be up here. So 2.9 is right here, and 0, 0 is right here. So the area is 0.0019. That's the area. So we write that down here. This is 0.0019. All right, and now we subtract them. So we take the bigger area, 0.4483, take away 0.0019. You get the area of 0.4464. So that's the area or the probability that the birth results in twins between 5 to 15 people.